My name is Martijn van Groningen, and we're going to talk about documents in a document-based storage. I work for ElasticSearch as an engineer to ElasticSearch itself. I'm also a Lucene committer. First, I want to talk about why you want to use document relations in ElasticSearch or maybe in any other document-based storage, and when to use it. And then I will go into the support ElasticSearch has, the parent-child, and the nested support. If we would take a look at this example data graph that shows relations between items in your data set, doesn't matter what. It can be people following other people, doesn't really matter. This is just the concept I want to explain. If you would index them as separate documents and you would like to have like some kind of a joining mechanism between it, and you started to run it on one machine, it will work out pretty well. So each document is indexed as a separate document, and some in-memory join happens, which makes it really fast. You see a client that makes a query, and an internal local join happens, and as long as everything's on the machine, it will be fast. But at some point, it doesn't fit, when the data keeps growing, it doesn't fit all in, on one machine. So what you want to add a machine to your small cluster. But how are you going to divide the data set? An approach would be to split everything in two. And you do a single request to a particular machine, and it will try to make a join. But in order to make a join, it cannot be a local join anymore. It needs to be a global join that goes, most likely, across the network to the other machine and tries to come up what matches with what. And as you can see, this won't scale well, because for a single request, you have many sub-requests. So don't do it like this. Another approach would be to use de-normalise. That's what we do in document-based solutions, right? Document-based engines. De-normalise your data set, and I try to visualize it here as one row, flattened row, which represents the normalized document. So instead of having a lot of small documents, you have bigger documents. Some of them are small, some of them are pretty large, depending on how much data it needs to include. Read-wise, doing queries, this works out fine. Request as fast. There's no join happening, because everything is already joined basically during indexing. And query is executed, it goes to the other machine, aggregates the results of both sub-requests, aggregates it, and sends it back as a result. However, reads are really fast. Indexing is a different story, because you need to, when you index, you need to most likely maybe have get data from different sources, maybe have a complex SQL join if you get your data from SQL, and make those denormalized structures. Also, what you end up with is a lot of duplicate data. So it would be nice if there is something that could minimize the amount of denormalized information. So if we could take a look at the data set again, most likely, in a lot of cases, not always, data is kind of, the relations are kind of isolated. They don't span across the whole data set. And if you have these groups of objects, of items, and group them together, you can basically group the related items together in a partition. And this partition you associate with a node. So in this case, we have two partitions, where based on this, data is being indexed to a particular side of the partition and to a particular node. And at query time, you do one query, and both nodes will do a local join without needing to cross the boundaries of the system, of the machine. This kind of join is maintainable. It scales, because if you can partition your data set and also the relations with it, you can grow to many machines in a cluster. And this is basically how, also in ElasticSearch, we work with a query time join. But there's something to remember is that you always will need to de-normalize, but how far do you need to de-normalize? That's the question, and you need to find the right side of the, what do you want to keep, what do you want to join at query time, and what you want to join at index time, basically. So dealing with relationships, either pay the price, upfront during indexing or during search time, and with document relations, we try to find a middle ground. For example, one join to reduce the amount of duplicated data you would otherwise have if you would de-normalize everything. I say one or maybe two or a few joins, but not tens of joins, of course, because it's not a database. It's a distributed system. It needs to be needs to scale. Also, one side note is that many-to-many relations is really hard to support in a distributed environment because those kind of relations typically span across a large part of your data set, and you cannot really partition it. So the only way to overcome this is basically de-normalize. So parent-child, it's the query time join in ElasticSearch. So let's go into this. So with parent-child support in ElasticSearch, you basically index parent and child as separate documents, and they are also separate types in ElasticSearch. In an index, you can have more than one type. It's like you can compare it maybe with a table in SQL, and you can make joins between them. A parent can be pointed by multiple children, and a child can only point to one parent. Also, a parent can also be a child of another parent, so you can create a kind of a hierarchy if you want to. Parent documents and child documents, they are indexed into the same shard in ElasticSearch, in the same partition. And the ID of the parent is used as a routing value to route it to the right shard. So everything is local, like I mentioned, with a local join. And because there's also an in-memory data structure that efficiently allows lookups for if this is a parent document or is this a child document, and look up if it has like a connection between each other. Makes it a really fast join. This is the data structure which is in memory, we have recently heavily reduced the size of it in 0.19.1. And because the data structure needs to be loaded in memory, and you can basically load it before query starts to run, basically via a warmer API. The warmer API is the ability to warm up indexes by specifying queries that run during opening of an index, basically. So how do you use it? Here above is an example of how to create an index. This is how you create an index in ElasticSearch, just a REST endpoint. And in this case, we're creating a products index. And we also associate a mapping with the index creation. So we create a mapping for the type offer. And we say here, type offer points to type product. Then at indexing time, which is the second snippet, this is an index. If you're not familiar with the index request in ElasticSearch, this is an index request. You index into an index and into a type, and you provide an ID. But in this case, we also provide a parent ID, so that this offer, which is a child, will be routed into the same shard where its parent is. And the request body is basically the document itself. So we only have 3 fields here. So just a simple example. The parent document doesn't need to exist at the time of indexing child documents. When you want to query this, at query time, you need to decide the join, basically, and you express the query time join, as a query in ElasticSearch. The hasChild query you define from what, or actually to what am I going to join. So you define the child type. The has parent, it returns parent hits based on matches or hits inside the child documents. So in this case, we define the query has child. We point it to offer, and we specify the query that runs on the offer type documents. In this case, it's a range query, and we're only interested in offers with a price lower than or equal than 50. And the result of this is all product documents that have an associated offer with this particular requirement. Optionally, you can also define a score mode, and that defines how the parent hits are sorted back to you. So how are the child documents, how are the scores from the query being pushed into the parent hit that's being returned. So that allows you to influence how to do the relevancy, basically, based on these hits. This is basically what I want to tell about parent-child. I mean, it's short. I don't have that much time. What I want to mention is that there's also a has-parent query, which does the opposite of what the has-child query does. So it returns child documents based on matches in a parent document. Okay. Let's go into nested objects. In a lot of cases, you de-normalize and you don't even need parent-child. I mean, parent-child you would only want to if some part of your data you want that to be, you want to separately update it or something like this, like with offers and products. Offers, they change more often than products, and that's why it makes sense to do something at query time to prevent heavy re-adding or re-indexing of data. But a lot of times you have kind of a domain model or like movies and actors, books and chapter. I mean, when you write a book, you don't. I mean, once a book is written, chapters don't reappear or are added to it usually, and it's kind of a static relationship. So what you do is de-normalize. And this nested object support allows us to de-normalize in a smart way. So let's take an example. Let's take an example of books and chapters. Here we have a book, or a JSON document that represents a book, with the title ElasticSearch, written by Clinton Gormley. He is actually writing a book. No pressure, Clinton. So, and I hope it will be released in 2013. So you have some properties, but we also have chapter data. And you see here, it's really denormalized to, well, as much as you can denormalize. Every chapter has its own title field, own summary field, own number of pages field. And I would say that is way too verbose. You can do it smarter, because we index in ElasticSearch data as JSON. And in JSON, you can just define objects, nested objects. And you can create objects in objects in objects if you want to. In this case, we have the chapters field, which is an array containing objects. And now it's denormalized in a much nicer way, because there's only one title field, only one summary field. And by default in ElasticSearch, each field is also at the same time an inverted index, so you can query it. In this case, we don't have that many fields than we had with the previous approach. The question is, how does this get indexed? Under the hood, ElasticSearch uses Lucene, so it's being translated into a Lucene document, which has no notion of hierarchies or nested fields or something like this. So this is what happens. The original JSON is basically flattened without the structure of the inner objects. And in some cases, this might not even be a problem for you. But if you want to have queries or queries to give me all books that have chapters that start with the title introduction, but have a number of pages lower than 15. This is when you cannot answer this question, but because the connection between those nested objects is lost. To overcome this problem, in ElasticSearch, you can use the nested field type. Like the create products index, when we created the products index, in this case we create a books index, and we associate the mapping book with the properties chapter, which is of type nested. And nested triggers some special way of indexing documents into Lucene called block indexing. By the way, it's also possible to have multiple levels of nested field types. Just like with the child type, you can also have kind of a hierarchy in this case. So, block indexing. What is this? Block indexing basically translates the ElasticSearch document, the JSON document, into multiple Lucene documents. So when we indexed, each chapter is an inlined document that is added just before the root document or the main document. And they always remain in the same order, and they are never taken apart from each other. And as you can imagine, this allows you to have it's a really kind of an efficient join you can do. If you know that everything is proximate, it's really close to each other, you can do a smart join. And that is also what in actually Lucene happens and what ElasticSearch uses. So, if you have the nested type and you want to use this specific way of indexing, you need to wrap your query in a nested query to point out at what level the join is. Obviously, you can specify multiple levels, so you need to tell at query time what level would you like to have to join. For example, we can have a book which has a chapter and which has a page level information. You need to tell at what level do you want to set the join. You do this with a pot option, and there is a score mode option. Just like with the hasChild and hasParent, there's a score mode. And this just defines how those individual inline documents, how the score is pushed to the main document. This query, it returns the complete document. It does not return individual nested hits, because for you, as a user of ElasticSearch, as far as you're concerned, it's just one document. And this nested type is only there to have a specific way of querying the data inside this nested object structure. Okay. Why is this join so fast? It's an interesting thing to explain. And I made something about it. I tried to visualize it. But I think in order for you to understand this, you first need to know about Lucene. In Lucene documents, so there's nested documents and this main document, they all get like an integer ID associated with it, which used internally into Lucene to reference to particular documents. For you as a user, it's not of your concern because you use the ElasticSearch ID, the application ID, to get data. But in Lucene, we assign integers to documents, and they are monotonic, meaning they start from a low value to a high value. This kind of identifiers can easily be represented into a bit set, because it's into a sparse data structure. So in our case, our example, the root documents, the real book documents, they are marked into a bit set, and the cross. It just tells you what the marked documents are. When the nested inner query runs, it goes in a particular order over the documents because everything's next to together. It goes basically from left to right over the documents. So when a child hit is matched, because there's a bit set that effectively easily can tell, okay, what is my next parent? So to what document do I need to push the score to? Can really easily and efficiently being done inside this nested query. That's what happens. So not all nested hits will match. Some of them, sometimes they don't match at all. So then the main document doesn't match in that case. And when you use one document match it, well, there's nothing to do to aggregate. But if multiple nested objects match, scores get aggregated. So depending on what your score mode is, which is either average, sum, or max, that depends on how the score gets aggregated and pushed to the parent document. Okay, this is the nested object support. I have 5 minutes left for questions. And if we don't have any, if we have time left after this, I have 2 extra slides that I can show about sorting in parent and child documents, how to do real sorting, and how to use the nested sorting, which is a relative new feature that has been added in 0.90. But first questions, if there are any.